Starting with the revision of the Fourier series, if we have a signal f of t, we can write it using the Fourier series. So we have a sum, n goes from minus infinity to plus infinity, of some coefficients c sub n times e to the I, which is the imaginary unit, times omega sub n times t, where omega sub n is equal to 2 pi n divided by t, where this t here is just the interval where the function f of t is defined. So we have some kind of function which is defined to be in the interval 0t. This is t, we have t here. The function is defined only inside this interval, may have some kind of strange pattern. It can be any kind of function, more or less. Okay, there are some technicalities here, but I will not get into the mathematical rigor that's needed to explain Fourier series in full details. What suffices here is just to say that I have an interval 0t where my function is defined, but the series representation also extends this function outside of the interval 0t by simply repeating periodically what's already in the interval 0t. So I have to extend the function outside that interval. So I'm trying to replicate what I did. Here I have, for example, the interval t to t. It's another interval with duration t. The function becomes periodically repeated after the application of the Fourier series. In any case, I'm just interested in what's happening inside this interval here, 0t. We can also work out what the coefficient c sub n must be, because we can multiply f of t by the complex exponential e to the I omega sub k t with a minus sign, and then we integrate it from 0 to t, capital T. And what we get, we have to multiply each and every term of this sum by this complex exponential. So we'll have a summation, and then we have an integral from 0 to t of some complex exponentials of the kind e to the I omega sub n minus omega sub k times t, where this omega sub n minus omega sub k, we can rewrite it as 2 pi n minus k divided by t, which is just simply equal to omega n minus k. So it can also still be written in this fashion. When we integrate such a thing, dt, this function here is periodic. You can see it from here because there is this 2 pi divided by t. So the period of the function is just t. This is the period. So the function repeats, of course, when we consider multiples of this capital T here. So we will get just simply 0 if n is not equal to k, but if n is equal to k, you get an integral from 0 to t of dt. So we get t if n is equal to k. So what shall we put here? On the right hand side of this expression, we will just have to put the only coefficient that remains after integration, ck multiplied by t, and we will proceed further in the next lecture.